Dear students, welcome to the second part of the fifth chapter. So in the second part we are going to discuss flow sensors. So first we will see the first category of the flow sensor, which is based on Doppler effect. So before this, flow is defined as the quantity of fluid or gas or liquid or vapor that passes a point per unit time. So it can be presented by simple equation. So flow is equal to quantity divided by time. So it is the rate of change of quantity. So it is either volumetric or mass flow rate. So this flow can be measured by employing the ultrasonic waves, where you will find the transmitter and receiver. So the main idea behind the principle is that the detection of the frequency or phase shift caused by the flowing medium. So one possible implementation is based on the Doppler effect, and another one is based on the detection of increase or decrease in the effective ultrasound velocity in the medium. So the effective velocity of sound in moving medium is equal to the velocity of sound relative to the medium plus the velocity of the medium with respect to the source of the sound. So in these two diagrams we can able to see the basic principle of flow meter. So figure A shows the ultrasonic flow meter position of transmitter and receiver crystals in the flow. So here A and B, these are the two modules which are mainly observed in the sensor. So either A is the transmitter or B is the receiver or vice versa, and D is the distance between the transmitter and receiver. In figure B shows the waveforms from these circuits. So in the first part it shows the transmitted pulse and the received pulse, where the change in the phase or change in the amplitude can be easily identified. So here upstream and downstream carrier frequency can be measured with the circuitry. So in the absence of or the steady state, the zero flow signal, so phase difference or the frequency difference or time difference can be measured to estimate the velocity of the fluid. So as I said, the figure shows the two ultrasonic generator positioned at the opposite sides of the tube of flow. So piezoelectric crystals are usually employed for that particular purpose. So each crystal can be used for either generation of the ultrasonic wave, that is motor mode, or for receiving the ultrasonic wave in generator mode. In other words, we can say that the same crystal, when needed, acts as the speaker or microphone. That is one module for the transmitting of the ultrasonic wave and another module to receive the ultrasounds. The next type of the flow sensor is based on the electromagnetic effect, that is electromagnetic flow sensor. So the electromagnetic flow sensor are useful for measuring the movement of the conductive liquid which is flowing through the pipes. So the operating principle is based on the electromagnetic induction effect. So when the conductive media, wire, or for instance for this particular purpose flowing conductive liquid crosses the magnetic flux lines, EMF, electromagnetic field, is generated in the conductors. So figure A shows the principle of electromagnetic flow meter, position of the electrodes at the top and at the bottom, that is perpendicular to the magnetic field B, and in the center we can able to see the conductive liquid surrounded by the coil. And figure B shows the relationship between the flow and electrical and magnetic field vectors. So here figure shows the tube of flow position into magnetic field B. So there are two electrodes incorporated into a tube to pick up the EMF induced in the liquid. So there are two kinds of or two methods for the inducing the voltage in the pickup electrodes. So the first one is based on the DC direct current method, where the magnetic flux density is constant and induced voltage is a DC or slow changing signal. So one problem of this particular DC method is that, so this method is polarization of the electrodes due to the small but unidirectional current passing through their surface. So this is the main problem of this particular DC method, that is polarization of the electrodes due to the small but unidirectional current passing through their surfaces. The other problem is low frequency noise, which makes it difficult to detect small, slow, or we can say that at the small flow rate this particular method will not give the proper results. The next method, which is working on the alternating current. So second better method of excitation is with an alternating magnetic field, which causes appearance of the AC voltage across the electrodes. So in this particular method you will find one transmitter with the specific frequency Fs, which is connected to the transmitter, which is located inside the tube, and the detector, which is connected to the amplifier. The received signal with the specific or the frequencies given to the mixer, and the mixed signals are passed to the band pass filter, which will give the frequency difference between the source and the received. So naturally the frequency of the magnetic field should meet the condition of the Nyquist rate, that is it must be at least 2 times higher than the high frequency of the flow rate spectrum variations. In practice, the excitation frequency is selected in the range of 100 Hz to 1 kHz. The next category of the flow sensor, that is breath sensor. So these breath sensors are mainly preferred when to detect the change in the air or any other gas for that matter movement, rather than to measure its flow rate quantitatively. So this particular sensor produces an output transient whenever the velocity of the gas flow happens to change. So in figure A we can able to see the piezoelectric breath sensor with the driver circuit. So FET based driver circuit, where the two sensors S1 and S2, piezoelectric sensors S1 and S2, are connected to the driver circuit with the bias resistance. And figure B shows the packaging of the typical TO5 can or bridge sensor. So a sensor contains a pair of the piezoelectric, sometimes the pyroelectric element based modules, where one is exposed to ambient air and other is protected by the encapsulating resin coating. So here S1 is kept in the ambient air and the S2 is coated with the resin material. So the two sensors are required for differential compensation of variations in the ambient temperature. So the elements are connected to the series opposed circuit, that is, whenever both of them generate the same electric charge, the resulting voltage across the bias resistor RB is essentially 0. An operating principle of the sensor is illustrated in this following figure. So here two cases, that is floating charge and during the gas movement, the polarities, so electrodes with positive and negative charge. So when airflow is either absent or is very steady, so the charge across the piezoelectric element is balanced, which is shown in figure A, or in the first case. Then the element internal electric dipoles, which were oriented during the pooling process, are balanced by both free carriers inside the material and by the charge floating air molecules at the element surface. So in the result, the voltage across the piezoelectric element S1 and S2 is 0, which results in the baseline output voltage V out. In the second case, when the gas flow across the both S1 surface change, S2 surface are protected by the resin, the moving gas molecule strips off the floating charge from the element, and due to this reason, this results the appearance of voltage across the element's electrodes, because the internally poled dipoles are no longer balanced by the outside floating charge. So here the negative charge are unavailable due to the gas movement. So the voltage is repeated by the JFET follower, which serves as an impedance converter and appears as the transient in the output terminal. The last category of the force sensor or flow sensor, that is drag force sensor. So the main application of such flow meters or flow sensors preferred for environmental monitoring, meteorology, hydrology and maritime studies to measure the speed of the air, water flow and turbulence close to the surface. So this is a typical arrangement for the drag force sensor. So here you will find the base for the flexible beam, and the flexible beam is attached to the drag element. So the movement of the drag element based on the pressure or the force applied by the particular flow of the liquid, and here on the flexible beam you will find the strain gauge, and strain gauge is connected to the signal conditioning circuitry. So here a solid object known as the drag element or target is exposed to the flow of liquid. The force exerted by the fluid on the drag element is measured and converted to an electrical signal indicative of value of speed of flow. So an important advantage of this drag sensor is that it can be made to generate measurement of flow in 2 dimensions or even in 3 dimensions as well as of flow speed. The operation is based on the strain measurement of deformation of an elastic rubber cantilever to which the force is applied to the spherical symmetrical drag element. So an ideal drag element, however, is a flat disc, because this configuration gives a drag coefficient independent of flow rate. But using spherical drag element which depart from the ideal of flat disc, the drag coefficient may vary with flow rate, and therefore the gauge must be calibrated and optimized for the conditions of the intended use. So the strain measurement can be performed with strain gauge that should be physically protected from the interaction with the moving fluids which is observed inside the fluid. So in this way the drag force sensor is mainly observed to measure the flow with the help of the strain gauge and the driver circuitry. So these are the various types of the flow sensors mainly observed in the instrumentation field or the embedded field.